Today's video covers Fourier series. Before we jump into what is a Fourier series or what is our goal for today, we're going to do a quick review from 11.1 from the last video that we had. One thing that we looked at was an orthogonal set of functions. We labeled them phi n of x, and so we used the inner product to determine that functions were orthogonal. And then we said if we have a function f that is defined on that same interval, we can expand f into a sum of those orthogonal functions, where c of n, so each of these coefficients, is determined using the inner product. So what we're going to do today is we are going to focus on an orthogonal set of trig functions, and it's the trig functions that are below. 1 cosine of pi over px, cosine of 2 pi over p x, so on and so forth. Also sine of pi over px, sine of 2 pi over px, so on and so forth. So those functions are orthogonal on the interval negative p to p. So what we're going to be leading to today is we're going to be having some function f of x, and we are going to expand that into some term a0 of n, and then we're going to be summing up from n equals 1 to infinity a bunch of those cosines. So this is just writing these cosines when n is 1, n is 2, so we're going to have n of them up to infinity, and a of n is just the constant out in front. And then we're also going to have to sum up those sines. We're going to use b of n for that, those constants. So what we're going to be doing is we need to find formulas for a0, an, and bn. Now, you're probably wondering, why do we have this a0 over 2? Why are we dividing by 2? It's simply for convenience. Simply for convenience, and you'll see when we get to that formula. So to find the formulas for a0, an, and b of n, we're going to start by integrating. So I'm going to take this formula above, which I know is orthogonal on negative p to p. So I'm going to integrate from negative p to p, f of x dx. This will be equal to, if I take out a0 of 2, I'm then integrating from negative p to p dx. And then I have this sum from n equals 1 to infinity. I take out a of n. I'm integrating from negative p to p of cosine of n pi over px dx, and then I take out the bn, and I'm integrating from negative p to p of sine of n pi over px dx. Okay, and so the question is, where does this lead us? Well, if we focus on this integral right here, that's same as the integral from negative p to p of 1 multiplied by cosine of n pi over px dx. And you're probably thinking, well, yeah, duh, why does that matter? Well, if we look at our functions above, 1 is part of that set. And so we know that 1 and any of those cosine functions are orthogonal, which means that this integral is just 0. It is a similar idea for this integral that has sine. That's really just 1 multiplied by sine. Again, those are orthogonal functions. So keeping that in mind, all of this will go to 0, all of that will go to 0. So what we end up with is the integral from negative p to p of f of x dx is equal to a0 over 2 integral from negative p to p dx. So if we simplify that right side, we get a0 over 2 times x from negative p to p, which then you can see we get a0 multiplied by p. Hence why we have this 2 for simplicity's sake. So then we have to remember on the right side, we have negative p to p of f of x dx. So our goal was to find a formula for a of 0, which we now have. That is 1 over p, the integral from negative p to p of f of x dx. So that is our first formula. So then, of course, we still have to find formulas for a of n and b of n. So what we're going to do next is we're going to return to the formula that we have above that I just starred. So we are going to return to the star, and we are going to multiply by cosine of m pi x over p, and we will integrate. So I'm going to have to move a little bit. I know that the formula went away, but hopefully you can see it. So when we do that, we get the integral from negative p to p of f of x times cosine of m pi over p x dx. And that gives us a0 over 2, the integral from negative p to p of cosine of m pi over p x dx, plus the sum from n equals 1 to infinity, a of n, we then have the integral from negative p to p of cosine of m pi over p x cosine of n pi over p x dx. We also have that b of n integral from negative p to p of cosine of m pi over p x and sine of n pi over p x dx. And I'm taking the sum of all of that. Okay, so again, we're going to have to ask ourselves, what do we know about this? Well, if we integrate a cosine function from negative p to p, we're going to get 0. And you can integrate that to confirm if you want to. We know that cosine and sine functions are orthogonal from above. So that is going to equal 0. So this goes away, and this goes away. So then the natural question is, what happens to this integral? So that's what we're going to focus on right now, is if we integrate negative p to p of cosine of m pi over px and cosine of n pi over px dx, well, that's going to give us 0 when m is not equal to n, and that's because, of course, these functions are orthogonal from above. So if the functions are orthogonal, so m is not equal to n, we're going to get 0. Otherwise, you're going to end up with p, and that only happens when m is equal to n. And you can integrate that to confirm, or you can just trust that that ends up being the case. So if we go back to what we have the integral from negative p to p of f of x cosine of m pi over px dx. That is equal to a of n multiplied by p. So where that leads us to then is that a of n is 1 over p, the integral from negative p to p of f of x times cosine of n pi over px dx. And actually above, instead of an m here, I should have written this as an n. And remember, we said that m and n are equal off to the right. So we now have a formula for a of 0 and a formula for a of n. Last thing we need is a formula for b of n. I'm not going to go through deriving it, but I will tell you that similarly, if we were to multiply, this time by sine of m pi over px and integrate, we would get the formula for b of n, which is 1 over p, the integral from negative p to p of f of x sine of n pi over px dx. So what we just did is we derived the Fourier series, and so on the next page we're going to formalize that with a definition. Okay, so here it is, the definition of a Fourier series. The Fourier series of some function that is defined on negative p to p is that formula that we wrote initially with these formulas for a0, an, and bn that we found. These formulas together are called Euler's formulas. And a quick note before we actually use them, this equal sign here is not a strict equal sign. What I mean is this is convergence. So f of x will converge to this expression on the right. It's not a strict equal sign. Okay, so now that we went through all of that deriving, let's actually take a look at an example. We are expanding f of x, so this f of x, this piecewise function, into a Fourier series. So looking at the definition above, remember we have to be defined on negative p to p, which in this case is negative 2 to 2. So if f is defined on negative 2 to 2, that tells us that our p-value is 2. If I start with my a of 0, we have the formula above, so I'm going to get 1 over 2. Now, because it's a piecewise, I'm going to have two different integrals. I'm going to integrate from negative 2 to 0 of negative x dx, and then I'm going to have to integrate from 0 to 2 of x dx. And so what that gives me is the first integral is negative 1/2 x squared from negative 2 to 0. And the second integral is positive 1/2 x squared from 0 to 2. And I will just tell you all of that ends up becoming 2. Okay, so next I'm going to do the a of n. A of n is 1/2. Again, we're going to have to split up into two integrals. So this will be negative 2 to 0 of negative x cosine of n pi over 2x dx. And then I have a 1/2 0 to 2 of x cosine of n pi over 2x dx. Okay, so we're going to have to integrate both of these, which are basically x and a cosine, x and a cosine. So you can do either integration by parts, or if you remember from class, we've done tabular. Tabular is a quicker way of doing integration by parts when you can take one term and differentiate it down to 0. The other term then you're going to integrate. So if I integrate once, I'm going to get 2 over n pi sine of n pi over 2x. And then if I integrate again, I'm going to get negative 4 over n squared pi squared cosine of n pi over 2x. It's a similar idea when we integrate here. So we have x, 1, 0, and then we already did the integrating, so I'm just going to copy them again. Okay, and then a quick reminder of how tabular works. We go along the diagonal, and we keep the sign and then flip the sign. So here we'll go along the diagonal, keep the sign, and flip the sign. Okay, so where that leads us to then is we get our 1/2. I'm actually going to write all this to the left because hopefully you can see this is going to end up being a pretty long expression. So we have that 1/2. The first time I integrated, I'm going to get negative 2x over n pi sine of n pi over 2x. And then I'm subtracting 4 over n squared pi squared cosine of n pi over 2x. And that is being evaluated from negative 2 to 0. And then that second integral will give me 2x over n pi sine of n pi over 2x. Add 4 over n squared pi squared cosine of n pi over 2x. And that is from 0 to 2. Whew. Okay, we've got some evaluating to do. Thankfully, we have some zeros. Okay, so when we plug in the zeros, I'm going to get 0 subtract 4 over n squared pi squared. So that's substituting in that 0. Then, when I substitute in negative 2, putting negative 2 into this sign, I would have negative pi x, so that's just 0. And then when I substitute in negative 2 to this expression right here, I'm going to get 4 over n squared pi squared cosine of negative n pi. So all of that is just the first evaluating. Now I have to evaluate the second expression. When I plug in the 2, if I plug 2 into this sine expression, so I plug in 2 for x, I'm going to get sine of n pi. Well, sine of any multiple of pi is just 0. So then I'll end up with 4 over n squared pi squared. Again, substituting in 2 for that x, I'm going to get cosine of n pi. Lastly, I'm going to need to substitute in 0. So the first expression will become 0, and then I'll be left with 4 over n squared pi squared cosine of 0, which is just 0. Okay, we have obviously a whole lot of simplifying to do. Okay, so first thing I want to notice is this term and this term are the same. So we end up with negative 1/2 times 4 over n squared pi squared, and there's another negative 1/2. So that's really just a negative 4 over the quantity n pi squared. I also then have this quantity right here. Well, 1/2 of the 4 will give me 2 over n squared pi squared cosine of negative n pi. And then I also have this quantity right here. So that will give me 2 over n squared pi squared cosine of n pi. Okay, so what do we do with those cosines of n pi? Okay, so what I want us to recognize is that these two are the same, right? And if you think about that, if n is 1, negative pi and positive pi, you end up at the same spot. Negative 2 pi, positive 2 pi, you end up at the same spot on the unit circle. And so what this ends up giving us then? When n is odd, we would end up with 2 over n squared pi squared, or negative 2 rather, and we would end up with another negative 2, which would give us negative 8 over n pi quantity squared. If n is even, though, on the other hand, then this quantity would be positive, this quantity would be positive, canceling out with that one, so we would get a 0. Okay, so what we've found so far, we found our a of 0. We found our a of n, which is also a piecewise function. And now, of course, we're going to have to find b of n. So our b of n, we're going to end up with 1/2 the integral from negative 2 to 0 of negative x sine of n pi over 2x dx, plus 1/2 the integral 0 to 2 of x sine of n pi over 2x dx. Okay, and similarly to what we did before, when we have the integral of this x multiplied by sine, we're going to have to do either integration by parts or tabular. So I'm going to do tabular. We have to differentiate down to 0, and then the other term we're going to have to integrate. So that will give us negative 2 over n pi cosine of n pi over 2x. And then we're going to get negative 4 over n squared pi squared sine of n pi over 2x. Similar idea for that second integral, x1, 0, and then I'm just going to copy over the function or the term that I already integrated. Okay, and then as a reminder, we go along the diagonal. The first one we keep the same, the second one we change. Okay, so where this gets us to then, again, nice long expression. That first one is going to be 2x over n pi cosine of n pi over 2x. Subtract 4 over n squared pi squared sine of n pi over 2x, and that is being evaluated from negative 2 to 0. I also then have the sum of negative 2x over n pi cosine of n pi over 2x, add 4 over n squared pi squared, sine of n pi over 2x, being evaluated from 0 to 2. Whew. Okay, we have some evaluating to do. When we plug in 0, we're going to get 0 here because of the x. If we plug in 0 here, we'll get sine of 0, which is 0. So we have 0 subtract 0. Then we need to substitute in this negative 2. If we substitute in this negative 2 here, we're going to get negative 4 over n pi cosine. If we plug in a negative 2 here, it'll cancel out, and we'll end up with cosine of negative n pi. If we substitute in negative 2 here, I'm going to get sine of negative n pi. Well, sine of any multiple of pi is just 0. Okay, so this first expression is done. I plugged in 0, I plugged in negative 2. We're now at this expression where we're plugging in 2 and 0. If we plug in 2, we're going to get negative 4 over n pi cosine of n pi. If we plug 2 into here, we get sine of n pi, which is just 0. So plus 0, okay. And then lastly, if I substitute in 0, I get 0 from both the cosine and the sine. Okay, so let's clean this up a little bit so that we know what we're left with. So this is 0, this is 0. So I end up with then 2 over n pi cosine of negative n pi, and we end up with negative 2 over n pi cosine of n pi. Okay, well, we already talked about before that cosine of negative n pi and cosine of n pi are the same. So coefficient 1 is negative, 1 is positive, which tells us we get our b of n to be 0. So I don't know if that is satisfying or frustrating that we did all of that work to end up with 0, but that's our constant. And so finally, last thing we have to do is put all of this together. So let's do that. On the right side, I'm just going to write down everything that we got for a of 0, a of n, and b of n. Okay, so now putting this all together, our f of x is equal to 1 subtract 8 over pi squared. I'm just factoring that out. The sum, n is our odds only, so from 1, 3, 5, so on and so forth, of 1 over n squared cosine of n pi over 2x. So the initial piecewise f of x function that we had above will converge to this summation on the right. So if we expanded that, we would get 1 subtract 8 over pi squared, and our terms would be cosine of pi x over 2 plus 1 over 3 squared cosine of 3 pi x over 2, so on and so forth. And so if we wanted to, we could write this a little bit nicer instead of having those odd ends. You don't have to do this. I'm just showing you how you could. It also could be written as 8 over pi squared. If we go from n equals 1 to infinity, those coefficients, so this 1 over 3 squared, that's 1 over 2n minus 1 quantity squared. And then we have cosine of 2n minus 1 pi x over 2. Again, you're not going to be asked to do that. You will just leave your answer in this form, which is great. Now, hopefully you can see this is a pretty long process. That's how it is. This is the one example that we had. At this point, you're going to have some examples or some practice to do on your own. We do have a few more things to talk about, though, before the video ends. So let's keep going. Next thing that we're going to talk about is convergence. So let f and f prime be piecewise continuous on our interval negative p to p. Then for all x that are in the open interval, the Fourier series of f is going to converge to f of x at a point of continuity. Well, the question, of course, then is what happens at a point of discontinuity. At a point of discontinuity, the Fourier series converges to the sum of f of x to the right and f of x to the left all over 2. So for the example that we just did, our series is going to converge to f of x at all x that are in that interval -2 to 2, and that includes x equals 0, because at x equals 0, it's not a point of discontinuity. Now, if you need a review of continuous and discontinuous functions, you need to look that up. Last thing for us to talk about is what is called a periodic extension. So we have all of these functions here that we already know are an orthogonal set. If we look at this function right here, just as an example, and find the period of it. Well, the period would be 2 pi over that pi over p, which gives us a period of 2p. Now, if we want the period in general of any of these functions based on their value in front, so the 1 pi, 2 pi, so on and so forth, the period in general would be 2 pi over n pi over p, which gives us 2p over n. So all of those functions have 2p in common in their period. 2p is what we call the fundamental period of sum. This gives us what we call periodic extensions of f outside of the interval. Okay, so let's see what that might look like. If we take a look at this Fourier series that we have in number 2, or this function f of x. So I'm already going to tell you what the Fourier series is, and you can go and practice it on your own if you want to. The Fourier series ends up being pi over 4 plus the sum from n equals 1 to infinity of 1 subtract -1 to the n over n squared pi times cosine of nx plus 1 over n times sine of nx. We might have a point of discontinuity at x equals 0. So at x equals 0, we notice when we plug in, we get 0. When we plug in, we get pi. So at x equals 0, we do have a point of discontinuity. So of course, we're going to know what happens at x equals 0. Our series will converge to f of 0 from the right, f of 0 from the left, and averaging them, which in this case, from the right is pi, from the left is 0, so it will converge to pi over 2. Now, taking in mind where we're going from -pi to 0 and 0 to pi, so here, our value of p is equal to pi. So what information that tells us then is that our Fourier series converges to pi over 2 at 0 and every 2 pi away from that. And that's because, again, our period has that 2p, and p is pi. So what we also want to do is we would also want to look at 1p in each direction. So x is equal to -pi, or we would want to look at x is equal to pi. So if we were to use the same idea that we used above, so -pi from the right and -pi from the left, and averaged them, we would end up with 0. And I'm going to put all this together in a minute, so just stick with me. So what that tells us is that our series converges to 0 at plus or minus pi, plus or minus 3 pi, so on and so forth. Okay, all of this is going to connect to a graph. So let's consider what this graph looks like. So if we want this to be pi, 2 pi, -pi. So if we go and graph what we have above, f of x is equal to 0 when x is between negative pi and 0. So that, I'm going to do it in a different color, that is right here. Then, between 0 and pi, we have pi minus x, which is right here. So that periodic extension that we talked about earlier just means what we can do is this graph is going to repeat every 2 pi, since that is our periodic extension. So we would have an extension there and then an extension here. We could go backwards. And so what we notice is at 0, like we found, we're converging to pi. When we go 2 pi away, we're also at pi. When we go 2 pi away in the other direction, we're also at pi. At negative pi or positive pi, we're at 0. Again, if we go 2 pi away, the periodic extension, we also get to 0. 2 pi away, we also get to 0. So this is the idea of a periodic extension. Where we're going with this, again, we're probably asking, why do we care? So far, what we've done is we've looked at functions that are defined from negative p to p. Well, what happens if we have a function that's defined from 0 to p instead? Can we still find a Fourier series? That's where this idea of periodic extensions is going to come into play. So I know this was a long one and quite a bit to go over. In the next video, we're going to be adding on and doing more with Fourier series. Please make sure that you do some practice on your own and that if you have any questions about what we did in class that you ask me. Thanks for watching.